Hey y'all, welcome back. So today's lesson is going to be a little bit of a review of what you learned in geometry as it pertains to right triangles. So most of this will be review, but it's going to set us up for what we're about to study not only in the coming days, but next year as well. So the first thing is the Pythagorean theorem. This is a theorem that you should be well aware of. There really shouldn't be any surprises here. This is probably the most famous theorem that's out there. You deal with this going all the way back to middle school, and basically what it says is that the square of each of the side lengths of the legs of a right triangle, those two squares sum is equal to the square of the hypotenuse. So I know that's kind of a word salad there, but I think if we draw a picture, it'll make a lot more sense. If you have a right triangle, meaning one of the angles in the triangle is 90 degrees, which I'll mark here with a little square. Okay, so if this is 90 degrees, then if we call these two legs A and B and the hypotenuse C, then the Pythagorean theorem essentially says that A squared plus B squared equals C squared. And this is a pretty powerful theorem. This really is where we get the distance formula from. In fact, the distance formula really is just the Pythagorean theorem in disguise. But there's a lot that we're going to do with this Pythagorean theorem. I know you're familiar with it, so I'm not going to dwell on this for too long. But basically, if you have A squared and B squared equals C squared, the sum of those two sides, or the squares of those two sides. Let me say that one more time. The sum of the squares of the two legs is equal to the square of the hypotenuse. Now, sometimes those sides could be integers, and when that happens, we call those Pythagorean triples. Okay, and we'll go over a few common Pythagorean triples here in a minute, but basically any time that you get set up here where A, B, and C are all whole numbers, then we have what's known as a Pythagorean triple. The most famous one is 3, 4, 5, right? Because 3 squared plus 4 squared equals 5 squared. But we'll go over a few more as well. Now we can use this Pythagorean theorem to solve triangles, specifically right triangles. And here's some examples of how you could do that. When I say solve a triangle, typically I'm looking for either the missing side lengths or missing angle measures, but here we're just going to look at the missing side lengths. So let's look at this first triangle. One of the legs is 5, the other is 12, and the hypotenuse is x. So using the Pythagorean theorem, we can set up an equation that 5 squared plus 12 squared equals x squared. And then we can solve this equation for x. We already know how to solve quadratic equations, so this should be pretty trivial. 5 squared is 25. 12 squared is 144. So we get 25 plus 144 equals x squared. And then if we add 25 and 144, we're going to get 169. And so taking the square root of both sides normally would give us plus or minus 13, but we're going to ignore the negative solution here because we are talking about the sides of a right triangle and the side lengths have to be positive. So the side length for this one's 13. Now notice how not only are the legs, but this hypotenuse is a whole number. So this 5, 12, 13 is an example of a Pythagorean triple. So this would make a Pythagorean triple. And I'm going to scroll down here just a bit to show you some other common Pythagorean triples. Okay, so we've got the 3, 4, 5 that I was talking about before. 5, 12, 13 is the one we just got. 8, 15, 17, 7, 24, 25. 9, 40, 41 is not that common. You won't see that too often, but that is one of the ones that has a small length for one of the sides. And there are infinitely many more. In fact, you could just scale up any of these triples to get even more Pythagorean triples. For instance, if I were to multiply each one of these by 2, I would get 6, 8, and 10. And those could be the side lengths of a right triangle as well. Same thing over here. This could be 10, 24, 26. And that would be another triple. So you could see how if we do that to all of these, we would get even more Pythagorean triples. And we don't have to necessarily just multiply by 2. We could multiply by any whole number. And so now you can see why there would be infinitely many different Pythagorean triples. But let's go back and solve this other one. Now, this one's going to be a little bit different in terms of how we solve it versus this first one, in that what we're looking for is not the hypotenuse, we're looking for the missing side. So this is going to be 7 squared plus x squared equals 14 squared. We do need to square both of these, so 7 squared is going to be 49. 14 squared is going to be 196. And then we need to subtract. So 196 minus 49, just to make sure I'm getting the right number here, I'm going to go ahead and use a calculator, is 147, which is not a perfect square. That's okay. So we get x squared equals 147, and if that number is not a perfect square, then really what we need to do is just estimate what x is. So we can do that by just taking the square root of this, using the calculator, and estimating. So the square root of 147 is going to be about 12.1. Okay, so I'll say x is approximately, and that's this little wavy equal sign, it's about 12.1. Won't be exact, but it will be pretty close. You can use your calculator if you want to get a more precise answer. This would not be a Pythagorean triple because 12.1 is not a whole number. So that's more or less what we need to know as far as the Pythagorean theorem is concerned. Now, there are some what we call special right triangles, and in particular there are two of them. The 45, 45, 90 and the 30, 60, 90 right triangles. So let me try to get a good sketch of each one of these. The 45, 45, 90 should have two angle measures which are equivalent, right, the two 45s, and it's also got this 90-degree angle measure. Just trying to make that a little straighter there. And then we have the 30, 60, 90. And we are not going to really see what's so special about these two quite yet. But in the very near future, we're going to see why we care about these two right triangles in particular. Now, what makes these special is that there is a particular ratio for the sides, meaning that if the angle measures here, in this case 45, 45, 90, okay, so here's a 45-degree angle, here's another one. I'm going to go ahead and label those just so that we're really clear. 45 degrees. And this other one up here will be 45 degrees. Over here, the smaller the two angles would be 30 degrees, and the larger the two angles would be 60. Okay, so like I was saying, there is a special ratio to both of these triangles. So for the 45, 45, 90 triangle, the ratio is going to be x to x to x times the square root of 2. So I'm just going to call it x root 2. And we can verify this using the Pythagorean theorem, and we can also verify it with a few other theorems that we'll get to eventually. So for right now, all I really need you to do is to remember these ratios so that we don't need necessarily to have 2 out of the 3 sides to solve the triangle. And that's what makes these kind of nice, is with the Pythagorean theorem, these other triangles that we solved earlier, we knew 2 of the 3 sides. Well, if we know just one of the sides, and we know that it's one of these special right triangles because we have some information about the angle measures, we can still solve it without relying on the Pythagorean theorem. So the ratio here is going to be x to x root 2. The ratio over here is going to be x for the short leg, 2x for the hypotenuse, and then x times root 3 for the long leg. Okay, so again, if we know that it's one of these special right triangles and we know just one of the sides, we can find the 2 other sides. So let's see a couple of triangles that we could solve using this amount of information. So for this first one, notice it's labeled as a 30, 60, 90. Okay, and we know the long leg is 9. So just to recap, if this is x, this is labeled y, but we're going to call this 2x. And then the long leg is going to be x root 3. Okay, so if we want to solve this, we're going to start with what we know. And in this case, we know that the long leg is 9. So if 9 equals x root 3, what we can do is we can divide both sides. If it'll let me copy this over, we could divide both sides by the square root of 3. And so x will equal 9 divided by root 3. And this is something we can throw into the calculator to get an estimate out. So x would be approximately 9 divided by root 3. You know what? Yeah, well, let's go ahead and just do an estimate for today. 9 divided by root 3 is going to be about 5.2. Okay, now when we go to find the y value, the y is going to be twice x here. So all we need to do is just double that number, and we'll get y. So y is 2x in this case, which will equal approximately, here we go, about 10. If I multiply that by 2, it should be about 10.4. Now for the 45, 45, 90, the two side lengths are the same, and this is x to x root 2 to x. So if this is my x root 2, this one's going to be pretty obvious. We don't even really need to solve an equation for this one because the side length's given in terms of root 2, so we can pretty clearly see that x is going to just be 2 here. Okay, now moving forward, there's going to be two specific special right triangles that are going to come up over and over again. And that is these two right triangles that have a hypotenuse which has a length of 1. So when you have a length of 1, for our 45, 45, 90, again, to scroll back up here, this is going to be the x to x root 2 triangle. So this is x to x root 2. So if I'm going to label that, if this is my x root 2, and here's x and x, I'm going to set up a little equation over here. 1 is x root 2. And then so to solve for x, I would divide both sides by 2, and I get x equals 1 over root 2. Now, it's been a little while since we simplified square roots, or simplified fractions that had square roots in the denominator. But what we really should do here is rationalize the denominator, and to do that, we need to multiply both the numerator and the denominator by root 2, and that will result in root 2 over 2. And so that's going to be my side length for x. Okay, so we've got this triangle here where the side lengths are 1, root 2 over 2, and root 2 over 2. Okay, it doesn't really seem that special, but trust me, this triangle is going to hang around for quite some time. Now, if we look at the one with the 30, 60, 90 that has a value of 1 for the hypotenuse, remember that the hypotenuse on a 30, 60, 90 is going to be 2x. The short leg is just going to be x, and the long leg is going to be x root 3. Or x times root 3. So we need to figure out what each of these are, and to do that we need to figure out what x is. So if 1 is 2x, then we can see pretty clearly, all we need to do is divide by 2 here. We get x equals 1/2. All right, so that's my x. That's going to be the short side here. And then my long side will be that number, that x, times root 3. So 1/2 times root 3 is going to be root 3 times 1/2, or root 3 over 2. Okay, so the ratio here, just to recap, was x to x root 2. Okay, and when that hypotenuse was 1, the ratio is going to be root 2 over 2 to root 2 over 2 to 1. Trying to kind of line this up as best I can here with I can't really do any spaces in here, so that's just going to have to do for now. Okay, so for the 30, 60, 90, I'll go ahead and box this because that's really what we want to focus on. The ratio here was x to 2x to x root 3. Okay, and in this case, my side lengths are going to be 1/2 was x. Okay, 2x was 1, and x root 3 will be root 3 over 2. You know, I'm kind of looking at these ratios thinking, you know what, 1's the biggest. Maybe we should put that last. So I'm going to actually just rearrange this a little bit. So it'll be more like the one for the 45, 45, 90. I'm going to put this 2x last here. Okay, there we go. All right, so this ratio here is extremely important. And I know I'm being kind of vague here purposefully, but trust me, with where we're going, you're going to see these numbers a lot, like a lot. So 1/2, root 3 over 2, root 2 over 2, 1. They're going to be extremely common numbers for us moving forward. Okay, moving on. Let's talk about trigonometric functions. This is something, again, that you talked about in geometry. And what trigonometric functions are there are actually a total of 6 of these trigonometric functions. Back in geometry, you only looked at 3 of them. And for today, we're still going to look at just 3 of them. But soon, not today, not tomorrow, but in the coming weeks, we will also look at the other 3. So the 3 that you've looked at so far are sine, cosine, and tangent. And what these represent are ratios of the sides of a right triangle. Okay, so let's consider this triangle over here. The hypotenuse is always going to be that longest side, the one that's opposite of the right angle. And then the other 2 legs we'll consider as either being the adjacent side or the opposite side. And these will both depend on which angle we're referencing. So if we were referencing this angle that's marked here as theta, I guess you probably can't see here. Let me just scroll up a little bit. This one right here that's labeled theta. Theta is this Greek letter. Looks like a 0 with a line through it. The adjacent side will be the leg that's next to it. So that is is one of the legs of the angle theta. And then the opposite side will be the side that's across from it. So if we were talking about this angle up here, then this side down here would be the opposite side, and the vertical side would be the adjacent one. So it all depends on how your triangle is oriented, which angle are you talking about, and as we do more of these this will be a lot clearer, hopefully. All right, so let's actually define these 3 functions. First, we've got the sine function. Okay, this is called the sine function. We also have the cosine function. And we have the tangent function. Okay, the sine function is abbreviated as SIN, and you'll notice you have a button on your calculator that says SIN, and that's what it's referring to. So sine of theta is going to be defined as the ratio between the opposite side and the hypotenuse. Okay. The cosine function is abbreviated as COS. So COS, that means cosine. Cosine of theta will be the adjacent side over the hypotenuse. So again, just another ratio of these 2 sides. Finally, we've got tangent, and tangent is defined as the opposite side over the adjacent side. Now in geometry, you may have been introduced to this acronym SOHCAHTOA, and all this is a way to help you remember what the 3 ratios are. So SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent's opposite over adjacent. So this, if you could just remember SOHCAHTOA and how to spell that, that can really help you remember which trig function matches with which sides. But these 3 functions will help us start to solve triangles with missing sides and angle measures. without having to use the Pythagorean theorem. Okay, so those are just definitions so far. Let's see how we could use this, and really we're going to be using this all throughout next semester. But first, let's just start to get used to these ratios. So we've got this triangle. Are you going to be able to see this? Let me just move myself here real quick, get myself out of the way. So we've got this triangle. It's a right triangle. The side lengths are 9 and 12, and the hypotenuse is 15. And it says, first find sine, cosine, and tangent of D. So D is going to be this angle right here. And if D is our reference angle, then the side opposite, I'll call this the opposite side, is going to be 12. And then the adjacent side will be 9. Now this is only going to be true for angle D. Once we start looking at angle E, those are going to be reversed. But the hypotenuse is not going to change. The hypotenuse is always the side opposite of that right angle. So sine of D will be the opposite side divided by the hypotenuse. So that'd be 12 over 15, which can be reduced, I believe, to, what would that be, 4/5. Cosine of D is the adjacent over hypotenuse. Wow, I just had a brain fart there. Adjacent over hypotenuse, which is going to be 9 over 15, which we're reduced to 3/5. And then finally, tangent of D is going to be the opposite over adjacent side, which will be 12 over 9, which will reduce to 4/3. Wait, is that right? Divide by 3, divide by 3. Yeah, 4/3. And so those are the three trigonometric functions for that angle. Now, if we switch it over and start talking about angle E, okay, these ratios will all be different. Okay, sine E is still opposite over adjacent, but if we're talking about angle E here, now the adjacent side is the 12, and the opposite side, so I'm just going to have to erase that and rewrite it. The opposite side would be 9. So for sine E, opposite over hypotenuse would be 9 over 15, which equals, if we reduce that, 3/5. Okay. Cosine of E which is adjacent over hypotenuse, is going to be 12 over 15. Here's the adjacent. I could have swore I wrote that, but I guess I didn't. Adjacent is the 12, and that reduces to 4/5. Now, something you might be noticing is that as soon as we switch the angles, the sine and cosine values reverse, and that's true. Okay, that is a good thing to notice here. Notice how, like, sine D is equal to cosine E, and cosine D is equal to sine E. It's interesting. Okay. Now, tangent of E is opposite over adjacent. So in this case, still looking at the same two sides, but since their reference is flipped, this tangent of E, opposite over adjacent, can be 9 over 12, which will reduce to 3/4. So these are all three of the trigonometric functions that we've talked about so far for both angle D and angle E, both referring to the same triangle. I'm going to erase these so I don't get confused because it is all dependent on which angle you're talking about. Okay, so now we're going to kind of push you a little bit forward here. It says use special right triangles to evaluate the following. We got 30, 60, and 45. So let's redraw these special right triangles. I'm going to go back up here. I guess I never really did draw them, but oh, here we did. Yes, we did. I'm going to just copy all this. So we have them nice and sketched out down here. Okay, here we go. And I'm not even going to fill out any numbers, okay, because this is going to be true for all 30, 60, 90, and 45, 45, 90 triangles. So the first one says, well, what's sine of 30? And I guess let me rearrange these so that The 30, 60, 90, the 45, 45 looks like is last, so let's move this guy over here. Oh, it's not going to let me do that. That's okay. That is okay. All right. So sine of 30. I'm looking over here at this 30, 60, 90 triangle. Sine is opposite over hypotenuse. Okay, so that'd be the opposite side over the hypotenuse, x over 2x, and if the x is reduced to 1, that just gives me 1/2. Okay, so sine of 30 degrees is 1/2. Cosine of 30. So if we're talking about 30 degrees here, okay, cosine of 30. Got it? We'll do tangents last, I guess, since we can't really fit all that in into one screen here. So yeah, cosine of 30 is going to be, cosine is adjacent over hypotenuse, so that would be x root 3 over 2x. And when we reduce that by, the x over x reduces to 1, so this is just going to be root 3 over 2. All right, now let's do the 60-degree angle measure. So 60 degrees is up here. Sine of 60 would be the opposite side over the hypotenuse. So that's actually going to be the same thing as cosine of 30. We noticed that earlier, that those should be the same. And so we get root 3 over 2 for that one. Similarly, cosine of 60 will be adjacent over the hypotenuse. So that would be x over 2x, which would reduce to 1/2. Now let's look at the 45, 45, 90. Now it doesn't really matter which angle you pick because look, the opposite and adjacent sides are the same. So sine is going to be x over x root 2. Now the way that this is going to reduce is going to be, well, the x's will cancel out. We'll get 1 over root 2. But what we really want is to go ahead and rationalize this. So I need to multiply both the numerator and the denominator by root 2. And that's going to leave me with root 2 over 2. All right, let me start boxing some of these answers. I didn't really do that earlier. All right, cosine of 45 is going to be adjacent over hypotenuse, and that should be the same as sine because both the opposite and the adjacent sides have the same length. So we get the same answer for cosine of 45. It would be root 2 over 2 again. All right, so now let's talk about tangent. This is going to be opposite over adjacent. So the tangent of 30 degrees would be x over x root 3. All right, this will be very similar to what we have over here, except it'll be over root 3. Okay, so that'd be 1 over root 3, which if I multiply that by root 3 over 3 would give me root 3 over 3. I think I may have misspoke there. I would need to multiply by root 3 over root 3, and that would give me root 3 over 3. Okay, tangent of 60 degrees, so that's going to be opposite over adjacent here, so that'd be x root 3 divided by x. So this will just be the reciprocal of tangent of 30, because the sides are just reversed. So this would be x root 3 over x, which means I have root 3 over 1, which would reduce to just root 3. And finally, tangent of 45 degrees, this has got to be the easiest one because both opposite and adjacent sides are the same. So this would just be x over x, which will reduce to just plain old 1. Okay, so there's a lot of problems just for these two triangles, but I did mention before, these numbers that we talked about up here in these ratios, root 2 over 2, 1, 1/2, root 3 over 2. We're seeing them pop up here, right? Look, they're all over the place with these special right triangles and their trigonometric values. So that about wraps it up for today. This is really just a little, mostly just a review of the trigonometry you covered in geometry, but also an introduction into the trigonometry that we're about to begin. So this is really good stuff. Thanks for hanging in there with me. Thanks for watching, and y'all have a great day.